I recently rekindled my electronics hobby and found Ben Eater's website. He produces educational kits and videos on various electronic subjects, including understanding digital electronics, microprocessors, computer architecture, and more. I bought his 6502 computer kit and began assembling it a few days ago. I'm a retired software engineer by trade, but I rarely thought about assembly language programming or how the CPU interacts with peripherals in a bus. Here is where I am with the assembly process. I'm currently stepping through each one of the videos assembling the components, programming the EEPROM with machine language, and clocking through each instruction. Ben really peels back the onion with his Building an 8-Bit Breadboard-Computer video series. While programming an existing microprocessor in machine code is at one level of abstraction that few programmers these days venture into, it's an entirely different level of abstraction to build a computer from the ground up out of discrete logic circuits. And this 44 video series shows you how to do just that. It's incredible. While the exercise will prove to be immensely valuable, I cannot imagine myself being able to finish such a monumental wiring task. The 6502 project is already challenging enough. So I've decided to add to Ben's body of work by re-implementing his breadboard computer on an FPGA. In this way, I get the opportunity to deeply familiarize myself with all the important concepts, but can do it in a less tedious way. FPGAs are always something I wanted to learn more about anyway, but have never had the opportunity. What is an FPGA anyway? Well, it's an acronym that stands for Field Programmable Gate Array. Field programmable means that the integrated circuit can be programmed each time it's turned on with code that defines the interconnected organization of a gate array. Okay, that sounds like a lot of mumbo jumbo. But what is a gate anyway? Well, it's something you're already familiar with. It's, not gates. It's AND gates, and it's OR gates, where you put inputs in and the logical operator operates and you get an output out. So field programmable means that you can basically redesign these circuits at runtime. And a gate array is basically a box with a bunch of arrays interconnected together. So you get the flexibility of designing your circuits in one chip package through software. It's really kind of amazing. Let's look at a simple digital circuit to get a better idea of what you can do with an FPGA. This is a half adder, and this is on the website circuitverse.org, which is a great resource for exploring digital circuitry basics. And it includes a modeling diagram capability that allows you to build simple logic circuits and then dynamically click on them to see their results. So this half adder, for example, if either A or B are high, the sum is high. If neither A nor B are high, the sum is low. If both A and B are high, then the carry bit is high. And this is basically a simple half adder. So what does this look like if you were to actually build it? Well, it looks something like this. I've got an exclusive OR gate and an AND gate wired according to the diagram we just saw. And if either A is high or B is high, sum goes high. If both A and B are high, carry goes high. Here is an FPGA implementation of the circuit that we just saw. We have our two input signals, A and B. We have our two output signals, sum and carry. And then we have the implementation. So sum is the exclusive OR, that's what the little hat means, of the A and the B signals. And carry is the AND of the A signal and the B signal. And so this language is called Lucid. It's invented. It's I guess you call it a language. It was invented by a company called Alcatree. The language is based on a hardware description language called Verilog, which is used widely in industry. It's a rather complicated language to understand. It takes a lot of training and experience to use well and correctly without error. Lucid is a superset, and it was built with the idea of trying to make, I guess, Arduino-like capabilities to an FPGA, which I think it succeeds in doing, because I found it very straightforward and easy to use. So here is the physical implementation of the code that we just saw. I've already programmed this FPGA with that code, and as you can see, in this case, our the A and the B inputs, it's kind of hard to see because these switches are darn small, but the A and the B inputs are the first two switches on this switch bank. And if I switch A, I get a sum signal. If I flip B, I get my sum signal. I flip both A and B, I get my carry signal. If they're both low, I get no signal. So basically implemented the same circuit as the physical circuit that we just saw in an FPGA using a hardware description language. So the first thing that I want to do is I want to try to implement the clock module from the 6502, well, really the Breadboard-Computer project, because it's the same clock module. I want to try to implement that in this FPGA as a starting point for this project. Let's get started reviewing the first version of the clock module. You can find the source code in my GitHub repository, located here, Chuck B, and the repository is Breadboard-Computer. And if you want to check it out, you can git clone it. Here's the instructions, and you just change directory. And then I have, for every one of the videos that are in this series, I've created a tag that corresponds to the video so that you can get the exact source code that is shown in the video. And you can do it with the checkout command as shown here, tags. And for this video, it's called clock-v1.o. So assuming you have that pulled down, or if you just want to walk along with me, you can. Why don't we first talk about what's going to be implemented. This is the schematic from Ben Eater's clock module that I purchased and I put together for the 6502 project, but he uses the same module for the Breadboard-Computer. So here's the schematic for it, and we're going to sort of walk through the signals and then try to translate those signals and gates into an FPGA implementation. So if we'll notice here, the signals, first of all, because we'll go look at how I've laid them out in the module. We have a halt signal, which is active high, and when that's high, none of the clock works. Everything is basically suspended. Over here, we've got the clock outputs. So that's the normal clock output, and that is an inverted clock output if you want to use it. Up here, then we have a manual selector switch that switches between automated, or I'm going to call it free running operation, and manual operation. Auto running when the signal is high, and manual when the signal is low. And then here is when you're in manual mode and you push this push button, you get one clock pulse, which allows you to advance the clock one clock tick at a time, which is really handy for debugging circuitry, or the CPU circuitry. And then here, there is a potentiometer that implements the clock speed. So, you turn it one way and the clock slows way down, and then turn it another and the clock speeds up. I'm not intending to implement it necessarily this way, although I haven't really decided, but I'll show you at least what I have, and then we'll go from there. So let's take a look then at some code that I've implemented. If you want to just follow along with me, we'll go over the signaling that's implemented in the module, and then I'll kind of walk through how this first version has been implemented. So, as mentioned, the clock produces two output signals, one a normal sort of output clock signal and an inverted signal. That's pretty straightforward. And it takes in 4 inputs similar to what we just described. So the period input is a 29-bit number that represents the divisor, if you will, of the number of clock ticks that are allowed to elapse before the output signal flips state. And this is a way to scale the clock, because in the Alcatraz AU board, there's a built-in 100 megahertz clock that runs all the time. So we're going to leverage that clock, and we're going to count some period number of times before we allow our clock to tick state. So that's what this value is allowed to hold, is basically the amount of the number of clock ticks that are going to allow to elapse before our clock will tick. And we'll talk a little bit about how that's going to be implemented a little bit later. Next input is the auto manual signal, and I call it manual B because B means bar, bar means low. So auto is high and manual is low. The next signal is the halt signal. So if it's high, the clock is halted. And then the next signal, advanced, that's the equivalent of the here, the manual clock control a signal. Okay, so here we have declared a signal of type signal, and in Alcatraz Labs language, I'm not even sure if you want to call this a language, but in any case, the Lucid language that Alcatraz Labs provides, they've declared a type called a signal, and the signal is best thought of as a wire. It sort of holds an internal, I guess, state, for lack of a better term. And what we're going to do is we're going to hold the current state of the clock in this signal. And why we're doing that is going to become apparent in a bit. Next, we have the clock and the reset signals being sent to a D flip-flop declared of 29 bits. And again, we want to hold this D flip-flop in this way because we want to be able to count up to whatever period has been provided into the clock. So this is going to this is going to contain a counter that will count up to this number. We have the scaled clock, and this represents the current state of our auto free running clock. Not to be confused with clock state up here. This clock state is really more geared towards what is the output of our clock module supposed to look like. Because remember, we have 2 ways to output the clock. One is a manual advanced clock and one is an auto clock. This scaled clock is meant to represent the auto clock, whatever the current state of the auto clock is. And remember, that runs at a different frequency than what our FPGA board runs at. So we're keeping this in the scaled down frequency internal, or clock state internal. Next is an edge detector. So we have a component that we've added from the Alcatraz Labs library called edge detector. And this edge detector is going to store the rise of the advanced signal. And this advanced signal will be triggered whenever this manual clock button is pushed. And we'll see how that's wired up here in just a bit. All right, so let's talk about our code. It's relatively simple, really. The first signal that's been wired up is the clock state. And remember, that's going to be the state that we want to show the outside world that our clock module is in. And this looks relatively complicated, but the way that you implement logic gates in the Lucid language is through traditional, what I would call traditional program operators. So the squiggle represents the not state. The ampersand represents the and, I should say not state, but gate. That represents the not gate. The ampersand represents the and gate. And the pipe represents an OR gate. And if you remember the schematic, let's flip back over there and look at that. This section down here are the gates that represent how we're aggregating the outputs from each one of these components. So we have our auto manual component, our clock advance component, and then the clock, the free running clock, that's this 555 timer with its clock speed. And so these gates here implement the combinatorial logic, if you will, of combining these three things together, which mirror the code, how I have this put together. So let's walk through this. So the clock state is a combination of these components here. So first is our halt signal, and halt is active high. So if we're halted, this is going to be a 1. So we want to negate that in order to output the clocks, any sort of clock state. So if we're not halted and either of these two conditions are true, we're going to output a high on our clock state. So let's look at this first condition. This first condition is if our auto manual bar signal is high, and remember auto is high in this case, and our scaled clock, the output of it is high, then we want our clock state to be high. That makes perfect sense. If we're auto mode and our internal scaled clock is high, then we want our clock state to be high, assuming we're not halted. Then on this side of the equation, if we're not auto manual B, in other words, if manual bar is active, and our advanced out signal is high, and remember, we created an edge detector that is triggered when a rising edge is high, called advanced. So if our advanced output is high, meaning that the user clicked the manual advance button, and we're in manual mode, and we're not halted, then output a 1 for our clock state. So this one line implements all of the logic gates that are listed down here, excluding this clock, inverted clock signal here, and I'll show you that in a second. But all these other gates, really right here, represent that line of code that we just reviewed. Let's go back and look at that line of code. So here's that line of code. Now we're going to wire that line of code, that's that internal wire, if you will, to the output of our clock module, which makes sense. Output bar, or the inverted, is basically just the inverted state of clock state. Now our internal counter, let's go back up here. We implemented an internal counter that created enough bits to create a delay for our auto running counter of up to 5 seconds running at 100 megahertz. Because again, the board's at 100 megahertz. And I just arbitrarily picked a number of bits that would give a pretty long internal delay. And I got 2 to the 29, and that's at least a 5-second delay. And so this code right here basically just implements our counter all the time. This bit of code wires up the advanced input to the advanced signal of our module, which makes sense. And we'll show how that's wired up to the button in a second. And then this last line of code checks our counter, our internal counter. And if it equals to the period that's been set as input, so that is basically going to give us 1 period's worth of delay for our free running clock signal. And if it's true, if it's equal, we set our counter back down to 0, and we invert our scaled clock signal. And whatever it is, it's high, flips to low, and vice versa. So this essentially implements the complete schematic that's depicted here, with a few exceptions. And I'm going to note those exceptions. You may have noticed, well, there's some debouncing that's going on here, and this 555 is not implemented at all in the clock module. Of course, we're using the clock that's already in the FPGA, so we're just going to take advantage of that. But these two 555 debouncers are not depicted in the clock module. And when I implemented this, I wasn't really thinking about it, but I'll show you how I did implement it here. Let's look at the IO. Let's look at the board for a quick moment. So this Element IO board is mounted to the top of the Alcatree AU board, and it provides a series of 8-digit LED displays, along with a whole bunch of LED banks split into 3. So there's 3 groups of 8, along with 3 groups of 8 dip switches, and then 5 push button switches, along with, on the other board, there's a reset switch that will do a global reset of the Alcatree board, as well as there's an additional set of LEDs that are on the Alcatree AU board itself. So let's go back at this, look at the source. So this example that I've modified here, the Alcatree Elements, I based this project on the Alcatree IO Elements board sample. And so that provides for you automatically these inputs and outputs. And you can see that they correspond to those are the 7-segment LEDs. It says right here on the comment, if I just read. So these correspond to essentially the anodes on the 7-segment LEDs. This corresponds to the digit select on the 7-segment LEDs. So all 7 segments are combined together, and then their cathodes essentially access to the cathodes are provided through these 4 bits on the IO cell output. The input then provides the 5 buttons push buttons we talked about. That's this input, and then the 3 banks of 8 dip switches are here. So this module then wires up switch 00, which is the far right switch of the far right bank, as our auto manual bar clock control signal. Switch 01 then is the halt signal. Button 0, which is the top button, is our manual clock control advanced signal. And then LED 00, which again is the far right LED far right group, that's our clock pulse indicator. So that's basically showing us what the clock is going to do. All right, so how is all this stuff wired up? So I mentioned that the clock module implements everything but the conditioners, the debouncers, if you will. The Lucid, or the Alcatree Labs software, provides 2 button conditioners, which are basically like debouncers. They're implemented as D flip-flops internally. So I've created one conditioner for the auto manual switch and another conditioner for the advanced button. Probably it made more sense to do this inside the clock module, but I wasn't really thinking that far in advance. And in a subsequent video, I'm going to re-implement this with these things built in so that you can give dirty signals to the clock module, and the clock module just cleans it up. So one thing to think about is the way that Ben, let's flip back over to the schematic for a second. So this 555 timer, when you click this button, provides a delay that corresponds to the RC timing constant that's been set up within this 555 timer. It provides a high pulse for just a little bit of time, which is fine. But in an FPGA implementation, the amount of time that we want to provide our pulse for is essentially going to be 1 clock tick of the 100 megahertz clock. Well, if you just hook that up to an LED, you're not going to be able to see that pulse, and you kind of want to. So, I mean, I think it's important to be able to see when you hit the manual advance button, you need to be able to see some indication that it actually is advancing through an LED. So what I've done is I've implemented a counter here that's going to essentially scale or hold for some period of time the manual advance signal so that you can see it on the LED. So a 2 to the 24th power gives you roughly 1/6 of a second on 100 megahertz board for you to see the LED. And I'll show you how that's implemented in a second. So here we've implemented our clock module because we're going to try to exercise it. And we want to hold the state of the manual advanced indicator LED. And that's what this D flip-flop is going to implement for us, is the current state of whatever this counter is telling us. As the counter is counting down, this is basically going to be the state of the indicator until the counter expires. All this code here is boilerplate. When you implement this project or create a project based on the Alcatraz AU board, you get all this code for free. So the bulk of this code then forms the implementation of wiring up the clock module to the Alcatraz IO board itself so that we can exercise it. So here we set the advanced hold counter to 0. That's the default state. So that advanced hold counter, which is implemented up here, advanced hold counter, always should be, the reset should always be 0. It should always be running essentially until we want it not to be running. And we'll show where that is in a minute. The advanced conditioner button, so that's the manual advance button. The input of it is going to be wired then up to IO button 0 as mentioned above. The auto manual conditioner input is going to be wired up to the dip switch 00 as mentioned already. So if our clock output, so if the output from our module, actually here, if this output right here, let's go down. So if that output is true, then we want to reset our advanced hold counter, and we want our manual advanced indicator to be flipped to 1. Now, why do you ask, do you want to do this all the time? Well, we're going to use some combinatorial logic to determine when we should do this. So for now, anytime this clock output goes high, we're just going to reset the hold counter, and we're going to flip the manual advanced indicator to 1. If the manual advanced hold counter's value is all 1s, and that's what this ampersand will do, it will take all of the bits that are sitting in this D flip-flop, and it will AND them all together. And if that's true, that basically means we've gotten to the top of the counter. And if that's true, then we're going to take the manual advanced indicator and we're going to set it to nothing, because we're going to flip it basically flip the state of it because we've gotten to the end of our internal counter. Now we're going to wire up the clock module itself. So we're going to wire the halt signal to dip switch bank 0, number 1. Our auto manual indicator or signal is going to be wired up to the output of the auto manual conditioner. The advanced signal of the clock is going to be wired up to the output of the advanced conditioner. Now for the period, I have just hard coded this to be roughly exactly 1 second. So that's on a 100 megahertz clock. This is going to provide 1 second of delay of free running flashing, which we'll show here in a second. Finally, we create some combinatorial logic to actually output the clock out to the IOLED 00. Now, why not just wire it up to clock out? Well, remember, if you manually advance the clock, you're only going to get 1 clock tick from the Alcatraz AU board, which is not going to be long enough to see. So this combines. So if we are running in manual mode, remember if we're running in auto mode, auto is high, we're going to AND that to whatever clock out says and just show it, because we're going to use the internal delay that we've hooked up as the mechanism to show whether the LED or the clock pulse should be of whatever duration that it is. However, if we're in manual mode, and remember manual is active low, we are then going to look to whatever the advance indicator is, whatever the output of that is, as set up above here to show the state of the LED. All right, so a lot of talking. Let's show this thing in action. So I've already programmed the board with this implementation. If you're new to this, this does a check of the errors to see if you've got any errors that are detectable by the Alcatraz IDE. The little hammer does the build. I'm not going to hit the build because it can take a minute or two to do. And then this down button arrow will put into flash. It'll put into a volatile memory the implementation. So I'm going to go ahead and hit that. And we get a done, which is great. So let's flip over to the board. And you'll notice nothing's happening. I have the board. So this dip switch here, this first one, is in manual mode, if you remember. So let's flip it to auto mode. Makes sense. First LED is now flashing at a 1 second period interval, which makes sense. And if I hit the manual advance button, which is the button here on top, you can see that it's basically not doing anything, which makes sense because it's in auto mode. Let's flip the halt switch, which is the second switch, and we should note that then the clock output stops, which it does. If I push the manual advance button, nothing happens, which makes sense because the clock is halted. Turn off halt, and it flashes again. Let's flip the auto manual button down to manual mode, and let's click the advance button, which makes sense. It's now advancing. If I hold the button, you can see that I get a little bit of visual feedback that it's actually pulsing. But of course, the clock output is not holding that long. It's only holding 1 clock tick's worth. And if I hook an oscilloscope up to it, we could probably see the pulse, but I'm not even sure my oscilloscope measures at 100 megahertz, so probably wouldn't be able to see it anyway. Just have to trust that that's what it's doing. So in the next video, what we're going to do is we're going to take this implementation and improve on it. We're going to bring these button conditioners and so forth into the clock module itself. And you'll remember that the speed implementation I didn't quite have working yet. If we go down here, you can see that the clock period was hard-coded. What we want to do is wire up probably a series of internal flip-flops to hold the state of our period and hook those up to buttons so that, maybe what we'll do is we'll hook it up to, these, maybe the top and the bottom buttons, so that if you click it, it will change the period by bit shifting, which bit is active for the counter to count up to. Like what you see? Don't forget to like or subscribe.